Okay. Well, I hope you guys are doing okay. I know around fifth weeks things start to well, I don't know. Maybe it started back in third week, but there you start to feel the tension mounting in the courses and whatnot. Just a few things about this class. I will post homework assignment 3 very soon. I've been trying to write it. It takes a while to write a good homework assignment that will be instructional in nature. So in homework assignment 3, I will walk you through the use of the function optim. Okay, so there's a lot of writing, and please just kind of read through it, and I hope the instructions make sense in terms of how to use optim, which is R's built-in optimization function, and you'll use that to try to minimize or maximize a few different functions, and then I've assigned a pair of problems from the textbook where you figure out Fisher information, and then I have some questions related to that. Today we're going to start chapter 3 in the textbook, and chapter 3 is entitled "The Bayesian Approach to Machine Learning." Okay. And so this is what's going on here with my screen. Week 5. Okay. So there's you can we're gonna spend just a few lectures on this topic of the Bayesian approach to machine learning. And I'm going to just kind of present this topic as maybe a little bit of a different paradigm as far as estimation goes and things like that. You can take an entire course devoted to this topic of Bayesian data analysis. There's, or not even just an entire course, but you can spend your entire career learning about this and developing this. And here we're just going to spend a few lectures on it. Next quarter, if you take 102C, we will do Monte Carlo methods, and Monte Carlo methods also factor into kind of Bayesian data analysis, and so that will we'll probably revisit this topic again as well. So if you take 102C with me, if you take 102C next quarter, it's going to be with me because I'm the only one teaching it, and but then we might have students from the other 102B class, and so there might be a lecture or two in there that are going to be very similar to today's lecture. That's okay. Let me talk about next quarter. I know a lot of you guys have been asking me about Stats 131, which is the course on Python, and I'm very excited to teach that. Although I don't know how we're going to do homework in that one. I have to figure that out. But I know it's not listed on the schedule of classes and things like that, and that's just because the registrar is being silly. We filed the paperwork to get the class added, and the registrar. It's held up on their end. Okay, we've done our part, and we're just waiting for them to get it listed and open to enroll. It's if you're trying to plan out your schedule, and I know a lot of you guys, your enrollment window is like your first pass is like in 10 minutes or something. What do you call it? The time is going to be scheduled for in the course scheduled classes. There's Stats 130 and then there's a time listed there. That's basically the classroom that we've reserved. And as soon as 131 gets turned on, we'll flip the classroom assignment there. So that's the classroom location. I imagine there's going to be a fairly high demand, and I imagine that many of you might not get in and will be disappointed. And I would just want to say, it's okay, all right? If you don't get into the class and you really want to get into the class, there's not much I can do because we're limited by the classroom space, and to be honest, you can probably teach yourself Python as well. You know, there's a lot of great resources, and so I don't know how great my class is going to be. Of course, I'm going to try to do the best I can do with it, but you know, I don't want you to feel like you're missing out on anything super great. We're just going to learn a little bit of Python here, okay? So let's be real. It's just one class. Okay. Well, anyway, let's talk the Bayesian approach to machine learning. Okay. The example that we're going to use is a binomial example for a coin game. Okay. And so the coin game works like this. You flip a coin, and you flip a coin 10 times, and if it lands heads 6 or fewer times, you win, okay? And so this is straight from the textbook, okay? If it lands heads 6 or fewer times, you win, okay? And so this is a binomial problem, right? And so the probability of getting X wins based on n flips, and for whatever reason they've used R, and probability of heads R. So basically we'd say P of X given, they used Y, of course, sorry. Okay, the probability of Y wins based on n flips, so probability of Y given n and R is going to be n choose Y, R to the Y, 1 minus R to the n minus Y. Okay. And I'm hoping this looks familiar from your days in, when do you learn this? 100A? This should be covered in 100A, right? Stats 10 also. Okay. All right, so this is what we have, right? And then, so in Stats 10, you would just you would get N and R and Y, and you'd plug them in, and you'd get an answer, okay? And then probably in Stats 100A, you had to figure out what R was based on the data that you have, right? Okay, and so, you know, we could say, well, if R is 0.5, then what's the probability of winning, right? If we have a fair coin, then R equals 0.5, and we can ask, what is the probability of winning? Okay. So in this case, the probability of a win is equal to the probability that Y is less than or equal to 6, which is going to equal to the sum of the probability of Y equaling I for I equals 0 to 6. So we have to say, what's the probability that you get heads 0 times, the probability of heads 1 time, the probability of heads, so on and so forth, up to getting 6 heads out of 10 flips, okay? Probability, I guess I should write Y equals I given n equals 10, and r equals 0.5. Okay, and then so you do something like 10 choose 0.5 to the 0.5 to the 10, plus 10 choose 1, 0.5 to the 1, 0.5 to the 9, plus so on and so forth, up to 10 choose 6, 0.5 to the 6, 0.5 to the 4, right? Or if we wanted to do this in R, what would we do? We could do a few things. We could do sum d binom 0 through 6, 10.5. And this is also equal, and I've run out of space to, I'm going to just write it, equal also to p binom 6, 10.5. Does that fit? Are you guys able to read that? So d binom is the density or the probability mass function, and then p binom is the cumulative probability, so it adds up everything from 0 up to the value you provided, in this case 6. All right. Is that okay with everybody? That makes sense? So if we, let me just queue up R here. Okay, so I could just do p binom 6, 10, 0.5. Okay, and we get 0.828, or I could do the sum of d binom. Well, first of all, I'll just show you what d binom 0 through 6, 10, 0.5 is. So that's, we have a vector of 7 numbers, and then I could just feed that into sum. Okay, and we get 83%. So if it's a fair coin, there's a 83% chance of a win, something around there. That seems like, oh, that's pretty good, right? But you're watching, you look at the carnival game, or whatever, this game that you're playing, and it seems like the carnival owner, or the game owner, is not doing badly, is not losing all of these games. So part of you suspects, you know, maybe the coin is not fair, or something like that, okay? And so you say, well, instead of just assuming that the coin is fair, what if I watched other people play the game, and based on the data that I observe, I will come up with a guess for the probability of landing heads. I'm going to try to figure out what R is, what's the probability that the coin lands heads, based on what other people do, okay? What's going on? Okay, so sorry, my pen is acting up. Okay, we will try to figure out the probability of getting heads for a single coin flip, which is R, okay? And this will be based on you know, data we observe. Okay, but let's say you watch 1, 2, 3, 6. Okay, so the first person plays. Okay, one person plays and gets 9 heads and 1 tail. Okay. And so you go, that's interesting. And we might say, what is the maximum likelihood estimate that will produce 9 heads and 1 tail? In a sequence of 10 flips. Okay. And so what we are dealing with here is we want to maximize the likelihood function. Okay? And so this is still not Bayesian. This is just maximum likelihood estimation. Okay? All right, and so the likelihood function this is a function of what? The likelihood function. So the parts that are given to us is our data. And the thing that we are going to adjust to try to maximize is what? Is R, the probability of flipping heads. Okay? So the likelihood function is a function of R. The data is given. And the given data is n equals 10 and y equals 9. Okay, so we want to know is we have a function of R, okay, and this is going to be 10 choose 9, R raised to the 9, and 1 minus R raised to the 10 minus 9, or in this case, 1. Okay, so this basically is the likelihood, or you can think of the likelihood as a probability, but it's the likelihood of our data for different values of R. Okay, and we can see what value of R would give us the largest value here. Okay, so we want to maximize this function. All right, so let's maximize it. Okay, and so what we're going to do is we're going to just take the derivative with respect to R and set that equal to 0. So the derivative of this, and we'll set it to equal to 0 and solve for R. Okay, I just want to pause here and just check in with everybody and make sure that this process makes sense. What the likelihood represents. It looks a lot like a probability, okay? Except it's because it's based on the density function, but it's not a density function. It's a function based on R, okay? Because for the probability mass function, you would change this value 9 and it only allowed for discrete values, okay? Either 0, 1, 2, 3, all the way up to 10. And if you added up all of those probabilities, you'd get 1. Here, we have a continuous variable R. R can be any value from 0 to 1, and it could be like 0.4476558, okay? It could be any type of thing. So this likelihood function is a continuous function going from zero, all possible values of r, which is in this case going from 0 to 1, and that's why we can differentiate it, right? If we tried to differentiate the probability mass function, you can't do that with respect to y. It's not possible to do that because it's not continuous. But here we can, okay? And then so if we try to do this, it's a little bit troublesome. So instead, we will maximize the log of the likelihood. Okay, and then so I'll just do that on the next slide. Something happened to my keyboard. Okay, so we have 10 choose 9, r raised to the 9 and 1 minus r raised to the 1, and then we'll take the log of this. Log of this thing, this becomes log of the value 10 choose 9 plus 9 times the log of r plus 1 times the log of 1 minus r. Okay. And then I'll take the derivative of this with respect to r, and so this is a constant, so that just disappears. And here I would get 9 divided by r plus 1 divided by 1 minus r times negative 1, right? So we can take the derivative of log likelihood. And then, okay, we set this equal to 0. 9 over r minus 1 over 1 minus r is equal to 0. Set to 0, solve for r. Okay, we get 9 over r is equal to 1 over 1 minus r. And then, what am I doing here? Why am I struggling with minus 9r is equal to r, and then I get 9 is equal to 10r, and I get 9 over 10 is equal to r. Okay, for some reason I just got stuck for a second. All right, okay, so we get r is equal to 0.9. And that makes sense, all right? So the maximum occurs, so the likelihood is maximized when r equals 0.9. Okay, and then I can illustrate this in R as well. Okay, so I'm going to just come over here. So over here, this was kind of our thing, and we could have asked, like, you know, all right, what's the so here I've got basically my function, I'll call f, or L, is going to be my likelihood function. This is a function of r, and what it's going to return is basically d binom of 9, 10, and r. Okay? This is equivalent to choose 10 comma 9 times r raised to the 9 times 1 minus r raised to the 1. Okay, so I could say, okay, what is the likelihood if r is 0.5? And then we get that. If I just commented this out, and I did this instead, we should get the same thing. Yeah, okay. So d binom just, for me it's easier to see it this way. Okay. Oops. Okay, so this is my likelihood function, and then I can just plot this. I can say x, we'll create a sequence, r, a sequence from 0.001 to 0.999 by 0.001. Okay, and then we will do the likelihood will be just run r through L, and then we'll just do plot r L type equals L. Oh, did I mess something up? Oh, not, of course. Okay. And this is our likelihood function, and we could see if the probability of getting heads is something around 0 or 0.2, it's very, very, very unlikely. The likelihood of getting 9 heads out of 10 is very low. And as the probability of R gets closer and closer to 0.9, the probability of getting 9 heads out of 10, or the likelihood there, gets really high, and then it drops back off. Okay. And then, you know, if we want to maximize this, we could just say which of the likelihood is equal to the max of the likelihoods, okay? And it says 900, okay? And then we can say, okay, well, which one, what value of R is 900? Oh, okay, and that is 0.9, okay? And so what we calculated in R also matches, and we see that it's maximized when R is 0.9. Okay, is that okay with everybody? All right, so this function, the likelihood function, okay, goes from 0 to 1, and at 0.9, okay, this is maximum likelihood. Okay, and then so based on this data, our estimate of R is 0.9, and then we can go back and answer the question, what is the probability of winning? Okay, so our maximum likelihood estimate is R equals 0.9. Okay, so we go back and ask, what is the probability of winning? I.e., getting 6 heads or less. Okay, and so here we would have to do, if I want to answer this in R, I would just do P binom 6, 10, 0.9. Because this is equivalent to doing 10 choose 0, 0.9 to the 0, 0.1 to the 10, plus 10 choose 1, 0.9 to the 1, 0.1 to the 9, plus so on and so forth until 10 choose 6, 0.9 to the 6, 0.1 to the 4. Is that okay? And so I go to R, I type in P binom, 6, 10, 0.9, my maximum likelihood estimate, and I get the probability of winning is only 0.0128. It's pretty low. Just want to make sure that the process that we've done so far makes sense. None of this has been Bayesian statistics, okay? This has just been, we looked at data, we used our data to get a maximum likelihood estimate, and we got our maximum likelihood estimate, and we're using that value to predict, or to try to answer our original question, what's the probability of winning? Is that okay? How do you feel about this process? Does it seem reasonable that the probability of winning is actually only 1%? And that, or is, I don't know, I guess the question is there anything about this process that makes you feel uncomfortable? Like, does this seem like a thorough analysis, like a good way to do this, or does something seem a little fishy, or something feel a little uncomfortable? Right, exactly, right? We've watched one person, and our entire estimate of R is based on these 10 flips. We looked at 10 flips, 9 of them were heads. We said maximum likelihood estimation, 0.9, boom, we're done. Now we're going to answer questions about the universe with this. It seems like, well, maybe we should observe a little bit more data or something like that, right? And I would agree, okay? In real life, however, it's always nice to say, oh, let's gather more data. And sometimes we can, sometimes we can't, right? And so what we are faced with is, well, let's say this is all the data I have. Am I ready to just rely entirely on the data I see? Or do I want to incorporate what we might consider prior knowledge, okay? And this is where Bayesian statistics comes in. Bayesian statistics says, okay, you have data. That is great, okay? Data is always useful. It helps us learn. But we shouldn't naively just go into the data and say, this is it. I've got fresh data. I've got an open mind. Here's my data. This is now my understanding of the world. What you should do is you should take your life experience and keep your life experience, and also incorporate the new data with that, and then adjust your, quote, beliefs about the world accordingly. Okay? And so maybe you go, you know what? I've never heard of a coin that lands heads 90% of the time. I'm not even sure if these things exist. Maybe they do, maybe they don't, okay? In my experience, most coins land heads 50% of the time, and I suppose it's possible that you can have a tweaked coin that lands heads at a different rate, okay? So this is the difference here, okay? So, and let me, okay. So is it already 4:40? Gosh, okay. I talk too much, I guess. All right. Okay, so your kind of the classical MLE approach is that our parameter theta in this case is some fixed unknown value, some unknown but fixed value, okay? And we look at data, use MLE to estimate R, and we use estimate R, which will be, I guess, R hat, and then we use R hat to answer you know, probability questions. Okay? The Bayesian approach is this. We have prior knowledge, or this could just be prior beliefs about theta, or r, whatever we're talking about. So we have some prior beliefs about theta, our parameter that we're trying to estimate. We take a look at the data. We look at the data, and we incorporate the data with our prior beliefs. Okay, this we get a new, I don't know, quote, belief about R, and we use that to answer probability questions. Okay, and when you look at this, you're like, well, that doesn't sound too different, but it is totally different, all right? Because the thing here is that with an MLE approach, the R hat up here, the biggest difference is R hat is a single value. Down here, the beliefs about R is represented by a distribution. What? Okay, hang on. Something happened. What needs to happen is I need to reboot my computer, but okay, give me a second. But I'm running out of time, so I don't have that luxury. Okay, here we go. All right. So beliefs about R are represented by a probability distribution of R. Okay. And so everything gets like weird and complicated when we do this, right? Because no longer because with the classical MLE approach, we just said, oh, the maximum likelihood estimate of R is that R is 0.9, okay? And you have a single value of R, and you just throw that into your equation, and you get an answer, okay? With the Bayesian approach, our beliefs about R are represented by a probability distribution, okay? So basically, now, if we ask what's the probability of winning, which is what's the probability that y is less than or equal to 6, this becomes, sure, 10 choose 1, or 10 choose 0, I'm sorry, yeah, 10 choose 0, r to the 0, r to the 10, plus 10 choose 1, r to the 1, times r to the 9, plus so on and so forth, up to 10 choose 6, r to the 6, r times 1 minus r, sorry, times 1 minus r to the 9 times 1 minus r to the 4th, okay? So we have that, except r now, r is not a single value anymore. It is a distribution. Okay, so how are we supposed to do this? Yeah, that's a good question. We have to do integrals, okay? Yeah, our favorite thing. So yeah, before r used to be something like 0.9. R is now, we have a probability distribution of R, and it's going to be something like, we think R can go anywhere from 0 to 1, and it looks like this. Maybe 0.5 is here, and but based on our data, it looks like 0.6 is the max, but also 0.7 is likely, or something like this. Okay, or so the probability of R could be represented something like this, or the probability distribution of R could be like, I'm very confident that it's 0.5, and it's very unlikely to be anything higher or lower. Or probability of R could be like that. There's all sorts of things. How do we do this? Okay. Basically, we have to now consider every single possible value that R could be, and we weight every single one of those possible values of R by the probability that R is that value. I'll write that out, okay? So the answer to what's the probability of winning, we'll now consider like every possible value of R. Okay, it's going to consider every possible value of R, and it will calculate the probability of winning for all possible values of R, except it weighs each of those probabilities by the probability of R. Okay, so we'll consider every possible value of R and weighs each of those possibilities by the probability of R. Okay. So what we have now is you have the probability that y is less than or equal to 6 is equal, and it's going to be the integral from 0 to 1 of basically for lack of a better way to express this, I'm going to just write p binom 6, 10, comma r. Is that okay? So this represents the probability of getting 6 or fewer without having to write 10 choose 0 plus 10 choose 1 plus 10 choose all the way up to 10 choose 6, right? Is it okay that I'm writing, like I'm mixing R code with math? Okay, so this just represents the probability of winning for any given value of R, okay? And then we integrate this across, we multiply this by the probability distribution of R. Probability distribution of R, and then we integrate this over all possible values of R, okay? So this is the probability of a win for a given value of R. This is the probability distribution of R, and this is going to be integrated across all possible values of R. And in this case, that means we go from R is 0 to 1. And this is going to be the probability of winning now. we haven't done any of the actual math. I'm just starting with this high-level perspective of what we want to try to do. Okay, and I want to make sure that this makes sense before we go on and start messing with distributions. Okay, so please take a look at this and make sure you understand, and then we'll continue on Friday. You'll also see a homework assignment posted very soon, and we'll see you then.